balloons in the lab kit?
Evidently, it seems like several people do not have balloons in the lab kit.
Okay, I just used a rubber glove, which, I mean, and rubber banded it to the top of the flask.
Okay. Hopefully that works with the balloon drop, now glove drop.
Yeah, I mean, we'll see. I kind of already have a concept of what it's supposed to do, so
Gotcha.
it should be fine. But I mean, it's filling with gas, so that's a good thing.
It sounds like it's doing more than Shane's is doing.
Yeah. Well, I rubber banded the fingers, so there wasn't as much area for it to fill up.
Oh, gotcha.
So, we'll see.
Okay. Well, is there something else you guys want to talk about? No?
Not really.
Not really. Nothing from chapter 4 confusing.
No, I haven't. I mean, I've got into it, but not far enough to really have a whole lot of questions. I'm a little behind this weekend stuff, so.
Okay.
Nothing really about the current chapters, but a little irked about myself because, like, I always take a really long time taking quizzes or tests, anything like that. I spent a little too much time on doing those molecule, balances.
Gotcha.
And it's like, thanks to that, it's like I wasn't able to answer the last 4 questions. Like, oh, come on.
Yeah, that's sad. That's like 10%.
Like, I should have just ignored those for now and just do everything else and go back to them.
Yeah, I think I just panicked on the test because it was timed. And so I flew through it. I didn't do well. But, I learned for the next one, I guess. So.
Yeah, it's just one. There's 4. Won't kill
Yeah.
you. It's only as worth as much as chapter review.
Yeah, so I guess don't be too hard on myself and do better on the next one.
That sounds good.
Yeah.
So I feel like, because we're in week 4, right? I'm not. There's week 1, there's week 2, there's week 3. Yeah, we're in week 4. I feel like we should do some chapter 4 discussion, but kind of up to you guys. Cammy, do you have any questions? Let me pull up the chat so I don't make sure I don't miss anything you're saying.
Can you hear me?
Oh, yeah. You don't need the chat. Totally hear you.
I've got you on my laptop now. I can't see you now, but I guess I can talk, so that's a good thing.
Yeah. Yeah. You can't see. What are you looking at then? Does it say Shane, Casey, Carbonian?
Believe it or not, it just shows your picture of you and your family.
Oh. I think if you run the mouse over the top of it somehow, maybe the thing up in the upper right hand corner that says speaker view.
Speaker view. I have gallery view.
Yeah, click on speaker, click on it. So click where it says gallery view.
Okay, I did that.
Do you see 4 people there now?
I do.
Okay.
You, me, Shane, and Casey.
Yep, that's it. That's just the 4 of us.
Okay.
And then when whomever is talking, there'll be like a yellow or a different colored box around them, so you know who's speaking at the time.
Well, I'm more concerned about seeing when you do equations and stuff like that.
Okay, so let me. Can you see a whiteboard?
I see you like in art now. It's all white, and I see the little pen.
Okay, good. All right, so let's do. Shane was saying he was having trouble with balancing, so let's just do a balancing problem. So we'll do C8H18 as a gas. I'm going to mix it with oxygen, and that's going to turn into carbon dioxide gas and some water vapor. Well, that should be vapor. Doesn't really matter though. Okay. So what I hope when you look at this equation, actually that looks terrible. Let me change that 2 so it actually looks like a 2. How do I erase? Pen. Okay, so what's wrong with this equation as written? Nothing? Nobody wants to say anything?
I have no idea.
Well, there's a whole lot of hydrogen missing for one. And carbon.
And carbons, like right here, this molecule has 8 carbons in it, and it has 18 hydrogens on it. The molecule kind of looks Are we getting the idea that there are a lot of hydrogens and carbons on this thing?
Yeah, and it looks like an easy molecule breakdown too.
So it's just carbons and hydrogens. There are 8 carbons here. So when this molecule goes to chemically react with oxygen, it's going to, all of the carbons are going to turn into the carbon dioxide molecule. Well, how many carbons are in a carbon dioxide molecule? 1. Just 1. Molecule is a carbon doubly bonded to oxygens. So where are all these 8 carbons going? How can these 8 carbons all of a sudden just turn into 1 carbon? The answer is they don't. You actually have 8 separate carbon dioxide molecules. Maybe I'll just... Sorry, I had bad penmanship, and it's even harder when I'm drawing on this little plastic thing on my desk instead of on a screen. So 1, 2, 1 more. So
yeah, some good drawing pads have actual displays on them as well.
Yeah, those ones were like $500+, and this thing was like $70. So that sort of made the decision for me. Okay, so what we needed to do is we needed to have 8 carbon dioxide molecules, so it would take care of all 8 of these molecules from the octane. So I need to put an 8 here. So what's happened so far is I've balanced out my oxygen, or my carbons. Okay, so what would you like to balance next?
The easy one would be the hydrogen.
Okay, so let's balance out the hydrogens. Man, that's harder than I thought it was going to be. So erase. Maybe I can do select. And then delete. Can I just hit the delete button? Oh yeah, that's much better. There we go. Okay. Go back up here to draw. All right, so that octane molecule had 18 hydrogens in it, and over here I've got a 1 water molecule. That only gives me 2. If I had 9 different water molecules, then I'd have a total of 18 hydrogens. Okay, so what I need to do is balance out my number of oxygens. On the right-hand side, I've got 16 oxygens here because it's 8 carbon dioxides, and over here I've got 9 oxygens in my 9 water molecules. And so that adds up to 25. That's kind of problematic. Does anybody know why that's problematic?
One more molecule than you should.
Yeah, I can't put, if I put a 12 here, that only gets me to 24. If I make that a 13, that gets me to 26, and neither one of those are 25. So the way this molecule actually reacts is anytime you get into a situation where there's an odd on one side and an even on one side, everything that you've already done, just double it. So this first one here, I'm going to put a 2 right here. And then I'm going to erase my 8 and erase my 9. This 8 turns into a 16, and my 9 turns into an 18. And because I doubled everything that I already had, then I know that the carbons and the hydrogens are still balanced. But now what I have are 50 oxygens. So then I can come over here and I can put a 25 in front of the O2, and I'm completely balanced out. Do you guys know what reaction this is?
No, not off the top of my head, but it looks like hydrogens and carbons, hydrocarbon.
So it's definitely a combustion reaction, right? Because there's an oxygen there. So this next chapter definitely talks a lot about how we get energy, and the most common way we get energy is by burning stuff. And so then you need a bunch of oxygen. And so this molecule over here, this is gasoline. This is octane. So if I put 25 oxygens into your pistons along with 2 octane molecules, then I'm going to get 16 carbon dioxides and 18 waters coming out the tailpipe. And obviously a bunch of heat and energy. Maybe this one was a little more complicated than we needed to start with. Let's do, why didn't that delete? Let's try a different one. How about just water molecule? So let's do, it takes hydrogen gas and oxygen gas, and if I put those guys together, I get myself a water molecule. Can somebody first tell me why I wrote H2 and O2?
So you have something to balance?
Nope.
And well, oxygen naturally occurs like that.
Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomics. Meaning when you find any of these 7 atoms in nature, they are always paired up. So chlorine, you can't just get Cls, they have to come as Cl2s. You can't just get Brs, they have to come as Br2s. So I'm trying to take oxygen and hydrogen and put them together, but they have to be paired because that's the way those molecules are found in nature as diatomics. Okay, so what's the problem with how this molecule or this reaction looks right now? Let's break it down a little bit more. I'll say we've got a hydrogen. What's going on here? I've got a hydrogen bonded to one hydrogen, and I've got an oxygen doubly bonded to an oxygen, and those two things together make this oxygen bonded to 2 hydrogens. Well, the hydrogens look fine. On both sides of the arrow, there is a pair of hydrogens. But the oxygens on the left side, there's 2, and on the right side, there's only 1. So that doesn't work. So what I need to do is balance this thing out. And in doing so, what I could do is I'm missing an oxygen on the right. So let me put another water molecule on the right. Okay, so I unbalanced my hydrogens, but I balanced my oxygens. So how can I balance it out completely? I put another hydrogen over here. So now when I'm looking at this, there are 4 hydrogens, and there are 4 hydrogens, and there are 2 oxygens, and there are 2 oxygens. Everything's balanced. And so if I'm going to write this chemically, I need to put a 2 in front of the H2 and a 2 in front of the water molecule. So what this is telling me is 2 hydrogen gases, 1 oxygen gas makes 2 water molecules. And when you make water from hydrogen and oxygen, that's what you need. Is that one a little easier?
Yeah, I understood that one.
Okay. Let's do a really easy one. So if dang it. If magnesium metal reacts with some chlorine gas, it's going to form magnesium chloride salt. That's terrible. What do we need to do with this formula? Is everybody okay with me saying that this is good as it is? There's 1 magnesium here and 1 magnesium here and 2 chlorines here and 2 chlorines here, and that's it. Everybody's been accounted for. So sometimes the equations just balance themselves and you don't have to worry about it, but that's kind of unusual. But the reason I'm calling that one balanced is because it has the same number of atoms on each side of each of the specific elements. Okay, something else?
Can I ask a question real quick about that?
Yeah, go for it.
So let's go back to the H2 plus O2, you know, with the arrow H2O, and we were missing the 1 oxygen.
Just a sec. Let me clear the whole thing off. Let me read. I'll just redraw it. I thought I could back up, but evidently I can't. H2, O2, H2O. Okay.
So the arrow just represents becomes or equals. Is that what?
Think about the hydrogen and the oxygen on the left-hand side as like water and flour. And then the arrow is after you've mixed everything together and baked it, and it's turned into bread.
Okay, I understand that. So I understand that we're missing an oxygen on the right-hand side. And you went into the bondings of the atoms below.
Yep.
Is there, because I that's kind of where I get a little hazy. Is there a way to just say, you know, we're missing H2 and then 1 O, and I know you added the 2 in front to double one side and the other. Can you just add a 2 to the side on the right to equal that out?
Can I just put a 2 right here?
Well, in front of the 2 H2. Well, no, because you missed. Yeah, so in front of the H, just put a 2 there.
To put a 2 right there in front of the water molecule?
Yeah, and that would equal it. Is that
Nope.
correct?
That's not right. You've fixed one problem and then made another problem, which is fine, but you're not done by putting a 2 in front of that. Because tell me again what that 2 in front of the H means, the H2O.
So is it 2 goes, I mean, I guess my math, you know, I keep thinking, is it 2 times 1 equals 2, and then 2 times the 1 of the 0 equals 2? Is that how the 0 is becoming a 2?
Do you see what I did there with the orange writing?
I do.
So that 2 in front of the water molecule means you now have 2 water molecules.
two H2Os.
Two separate
Okay,
H2Os.
not
So
just an O, but two H2O.
two
Okay. Oh, I get it.
this 2 right here, this guy does not apply to this hydrogen. It applies to everything after it, which is the very different from this 2 right here. Only applies to the hydrogen. It has nothing to do with the oxygen. So this molecule, written as H2O, is an oxygen that's connected to 2 hydrogens. That's what. So go ahead.
I understand it. Okay. Okay. So the H2, the 2 only affects the H, where the 2 in front of the H2O makes two H2Os.
Correct.
I get it. Okay.
So
Okay. Yeah.
so this thing must have been really confusing.
No, I was going.
So now what is that? Now that you understand the water part, tell me what this thing is. It's a molecule that has what connected to what?
It's a molecule that has what CH or C8H18.
It's a molecule
So
that
it
has
eight carbons and 18 hydrogens.
all connected. And I drew that thing up there. And that
Yeah.
molecule that I drew up there had 8 carbons in it and another 18 hydrogens connected to it. And that's the whole thing. So this 8 was referring only to the fact that there were 8 carbons, and this 18 was referring to the fact there's 18 hydrogens all connected to the same molecule. If I put a 2 in front, what does that mean?
It means 16 carbons and 32 hydrogens.
Yes,
Correct.
and I'm not 100% sure you have it. What it really means is it does mean 16 and 18, but it means 2 separate molecules. It does not mean C16H32. Do you see the difference?
Oh, I understand what you're saying. Okay, so it's 2 of those.
Right. Not a molecule
Two
that's not a molecule that now has 16 C's on it and 32 H's.
Think that it has like invisible parentheses around it.
Sure. Like this is all here, and then those guys are all inside there, and this is getting really messy.
Okay. Okay.
Does that make sense?
Yes, it does.
All right.
I would like to actually, I think that was kind of why I struggled on some of the computations in the first, the first and second chapter was, is there a place where we could do more examples of our computations to make sure we understand how it works? Because when you're reading, I mean, I'm reading through the chapters and I'm taking notes, but sometimes it's hard to grasp what they're doing just from the book.
So like if you're let's find a spot here. Let's look at say
Yeah, the critical thinking, the blue question boxes.
yeah,
Ask you to use some of these.
so when you're sorry, I'm trying to find so like okay, so if you're do you have a textbook?
I do.
Okay, so if you look at page 35,
Page 35. Okay.
Yeah. so that's section 1.8, and it's the
Yeah.
section that's trying to introduce how to name molecules.
Yes.
So you'll read through that, and they give you some examples, but then on page 36, there's a your turn 1.3 in blue.
Okay.
So there, that gives you a chance to answer those questions, and then the answers are literally right there. So if you, I don't know, take a piece of paper and cover up where the answer part is and just try to answer those inside those your turns, then that's sort of, they're trying to, like, this is the type of question you get based off of the information that you just read.
Okay.
And so like the same thing happens with that 1.4 talking about the hydrocarbon naming. So the molecule that I just put up there, the very first balancing one we did that was a little too complicated to start with, that molecule is called octane. So look in table 1.6. Does that name make sense?
1.6. What page is that on?
36.
Octane?
Yep.
Well, isn't oct-8?
And so look on the whiteboard on the screen now. That was the molecule C8H18, and the 8 literally is referring to that.
Okay. Oh, okay.
So if you had, I'm sure you know the molecule name propane. So what does prop mean from the table?
From the table is 3 C atoms.
And this is the propane molecule, C3H8.
Okay.
And so that little section down there at the bottom of page 36 in blue, it gives you a chance to try to do that, like help name those things. And then also all the answers that are even are in the back of the textbook. So if you go to the end of each chapter and find some questions that you aren't able to answer, you can attempt them and then go into the back and try to get the answers for those. So like if you turn to page 60, say,
Okay, and do some of those.
yeah,
the
say like
evens.
question number 20, it wants you to balance that equation. Do you recognize that first molecule in 20A, question 20A?
28. That's at C3, which is the prop, right?
Yep, that's the propane. This one we were just talking about. So then
Okay.
if you take propane molecules, I mean, like what do you do with propane molecules?
What do you do with them?
Yeah, what do you personally do with propane molecules?
Use it for energy.
Yeah, you put them in a barbecue right there, the bottom part of the barbecue grill, you cook your food with it. So though that is something you can use to combust, and it's a hydrocarbon. So if I take, keep doing that. If I take C3H8 and I mix it with oxygens, I'm going to make carbon dioxide and water molecules. It's the exact same thing that you're going to make if you burn gasoline. So tell me what's wrong with this equation being balanced. How is it not balanced?
There's less C's on the other side.
On the other side, I'm missing 2 carbons. Okay, so how do I fix that? When I burn propane, I must not make 1 carbon dioxide molecule. I must be making how many carbon dioxide molecules?
We'd have to make 2 more, right?
You have to, yeah, make 2 more. So that's saying you have to totally make a total of 3. So
Yes.
if I put a 3 right here, what that really means is that there are,
CO2.
that 3 means there are
3 CO2s.
3 CO2s total. Does that make sense?
Yes, it does.
Okay, so why do you think we write 3 CO2s? Because this would be a pain in the butt, right?
Yes.
In algebra, you don't write like A 27 times an equation. You just write 27A. And that would tell you how many A's are in the equation. You combine all the like terms. And that's what this is. This is just combining. This is saying, we've got 3 of them, but I'm not going to write it 3 times. I'm going to tell you that there are 3 of whatever comes next. So the left side of the equation over here, the reaction side, we're saying I've got 1 single molecule and that molecule has 3 carbons in it. But when this stuff burns, this molecule breaks up into, all the carbons are separated. So they come out as 3 separate carbon dioxide molecules. Does that make sense?
Yes.
Okay. So what else happens? Well, the propane molecule doesn't stay stuck together at all. All the carbons get torn off and all the hydrogens get torn off. So this propane molecule started with 8 hydrogens connected to it, but now the molecule is completely torn apart and it ends up turning into water molecules. So this water molecule that I have over here, how many H's does it have in the one water molecule?
2.
So how many separate water molecules would get me to 8?
How many separate how many separate H2Os?
Would get me to 8 H's.
So because there's 2 there, so you just say 6, right?
No, how
'Cause
many?
you have 2 hydrogens, right?
If I had,
Oh, you mean okay?
if I had,
6.
no, if I had 6 water molecules, that would only that would give me 12 hydrogens because each of them has 2 hydrogens on them.
Okay.
So how many do I need? Let's do it this way. Let me write. Let me do this. Let's erase that for a sec, and let's make this as descriptive visually as possible. So, you okay with that?
I'm good with that. Yes.
Okay, so why did we do that? Because this molecule here on the right, the propane molecule, had 3 carbons in it, and I have to account for every single atom. Think about these molecules being Lego structures. So you created this Lego structure that had 3 red Legos and 8 blue Legos, and you're going to completely disassemble it and build stuff. And you have to use every single one of the Legos. So now what you did is when you ripped this Lego structure apart, you made a new Lego structure that each of the new structures had 1 carbon on them. So now you've used all 3 of the carbons that you started with. Does that make
So
sense?
now your C3s are balanced. Yes.
So now my carbons, I had 3 in one molecule. Now I've got 1 in 3 separate molecules, but I have 3 on each side of my arrow.
Yes.
Okay, so I know I've got 8 hydrogens I have to take care of over here. Well, the carbon dioxide has no hydrogen in it, so it's all got to be accounted for by the water. So let's say I added another water molecule. How many hydrogens do I have now?
4.
That's not enough. Another one?
6.
That's
And
not
then-
enough.
Oh, okay. Yeah. Okay. Yeah.
So
Okay.
when you burn propane, when you pull out your barbecue grill and you're cooking up some hamburgers, every single time a propane molecule gets burned, what gets made?
Every time it gets carbon dioxide or
3 carbon dioxide molecules and
8 H2Os
no
or
4
8 H's.
4
Or
4 H2Os. Right?
Okay.
Does that make sense?
Yes.
Okay, so
I think when I'm under less pressure and I'm doing this, I'll be able to figure it out. Because
okay.
I understand now how you're doing it. You have to write them all separately and then add them up that way
This
to balance them out.
what I just did right here was separating all those. I was doing that when I was first figuring out how to do this. But later on you won't do it. You'll like think about it in your head and then you can just put the numbers in front. But
Okay.
we have one more thing to do. How many oxygens are on the right hand side total between both those sets of molecules?
So you got 6, right? By the CO2s, you got 6 there.
Yep.
And then you've got 1, 2, 3, 4 on the H2O side.
Yep. So
Right.
how many total?
10.
Okay. So you made 7 molecules, and those 7 molecules have a total of 10 oxygens in them. That means when you started, you must have started with 10 oxygens. Right now we're not showing that. So how can we show that?
Put 10 in front.
Not 10, because each one of these has 2.
5.
5. So
Yes. Okay. Yeah.
does this all looks good?
Yes.
So then what we can do to make it look like the way a chemist would do it is I would put a 5 here, a 3 here, and a 4 here, and then
1, 2, 3, 4, H2. Okay.
delete. So I can write it all in one line.
I keep trying to, for some reason, it's been a long time. I keep trying to take like the 5 times the 2 to make 10. I'm like going back to, but I get what you're saying. I need to write those all out until I understand it, or make sure it's balanced on each side.
Correct. So having practice with that, what you can do is look down at like chapter 20, or sorry, chapter 1, number 20, and that's the problem we did. The answer for that is in the back.
Okay.
All 3 of those, 20A, B, and C. I don't think 21 is because it's an even number one. 23 is not. I could definitely post more stuff if you just want more stuff.
Well, I don't think anybody else needs it but me. It's just been years since I've dealt with this.
You are completely incorrect about that. I guarantee you there's 35 people taking this class right now. You just said that, and whomever is watching, let's say the entire class watched this video, minus the 4 of you who are here, half of them would be like, yeah, I would do that too. Every time. Every time somebody asks a question in my face-to-face class, there's 5 to 10 other people in the class that just didn't ask it, but they want to know the answer to it. So ask as much as you want and ask for as much as you want, because there's guaranteed that you're not the only one who wants that stuff.
Okay.
Okay. What else we want to talk about?
Oh, thinking back to the molecules, like it's like we probably haven't covered that by adding into the equations at all, but some molecules naturally react with each other.
Sure.
Now the ones that need external energy, how do you like apply that to the equation if you want to show it on paper?
You mean like the balanced chemical equation?
No, it's like with like with the hydrocarbons and oxygen and whatnot, it's like it needs external energy to get the reaction started.
You wouldn't show that in the equation, but for all the common and many uncommon equations, somebody has figured that stuff out. But that's nothing that we're going to talk about in this class. That's for a different class, probably. That'd be 122 or 212, either of those classes, because the subject you're talking about is called thermochemistry, and it's the heat associated with that you get from a reaction and you put into a reaction. So that we're not going to deal with that.
Okay. And I just checked my lab. Just a bunch of white foamy looking stuff on top, and balloon barely changed at all.
Okay. Mm-hmm.
I think I may have got some balloons that are a little too thick.
Oh, I see. Best place for cheesy balloons, dollar store. Aurelia, do you have any questions?
No. I'm just getting started with chapter 4, so.
Okay.
I have kind of a cheesy question.
An actual question about cheese?
Do you suggest, again, it's probably been 30 years since I've taken chemistry, so do you suggest that we memorize the periodic table of elements?
Nope.
Because I know that a lot of times, the book or you will talk about something that I'll have to look up on the table to see what it is.
That's totally fine, because I would never be without a periodic table.
Okay.
Whenever you're doing chemistry stuff, what I would suggest is you have a periodic table. like right there, either like hanging on something or readily available that you can just grab, or maybe open on a window on your computer if you're working on computer stuff, so you can just pull that thing up immediately. But I've always got one on me. Like, that might sound weird, but my phone has a default periodic table on it that I could just pull anything up immediately. But
Well, I printed one from the internet, and I've have a ton of notes on it. I just think one of the things I get screwed up about on is the terminology symbol, element, or atom. Like, I noticed that those are used interchangeably.
sometimes, yeah.
Are they the same thing?
No, it's it's us and the English language being difficult is really the issue. They technically mean different things, but they're not mutually exclusive of each other. So, sorry, what the terms were? What'd you have?
Like symbol,
let me write.
element, and atom. Like I noticed, like on my table, my periodic table, you know how you had it, or you showed us that it was broken down into groups like 1A, 2A, and then there's the B's, and then the 3A, you know, across the top. And I understand that the groups like 1A, those groups all have one atom, correct? And like the 2A's are all 2 atoms, and then over to 3A's like that, right? So I was
Oh, no,
assuming
that was those were electrons we were talking about, not atoms.
the outer electrons.
The outer electrons, yes.
So what does the A represent on 1A? That's the group name.
Oh, it's just the group name. So there's a section. Does the periodic table that you have, does it say 1A and also say just 1, and next to it says 2A and 2 above or below it?
Yes.
So the old nomenclature for naming the groups on the periodic table were 1A, 2A, and then you skip from the second column all the way over to the column with boron in it.
And it's 3A.
That's 3A, 4A, 5A,
8A.
up to 8A. And in that
Yeah.
lowered section, that has like iron and copper and whatnot in it, those are all classified as Bs. All right?
Okay.
So that's an old way to do it because they were trying to make sense of some stuff. But the newest periodic tables, it literally says 1 through 18.
Okay, yeah, I don't have that one. I think wrote down my notes from in chapter 1, I think, where it explained the groups. So I think I took this periodic table and wrote down what it had on that table in our book.
Okay, so
yeah, it's
you have the textbook though, right?
I do.
Open
Yes.
open the back cover.
Yeah, I did know there was one there, but I wanted to be able to tear it off and
Sure.
look at it like you said as I did my homework. That's why I have this other one.
Right. I just want you to notice that on that table on the inside back cover, it says the very first part of the table says 1, and right underneath it says 1A.
Yes.
And then you go all the way to the other side and it says 18 and 8A. So all I'm saying is they're just two different ways to talk about the numbering of the columns. And when maybe 20 more years passes and during those 20 years some old chemists die, it'll just be all the tables will just say 1 through 18.
1 through 18. Okay. But like you said, the A doesn't stand for anything. It's
a classification system. So
Okay.
with the A's, the charge that the atoms in columns that have A's next to them is fairly fixed. Not 100% fixed for all of them, but fairly fixed. And the ones that have B's as their column headings, the oxidation state or the charge that they make in a compound can be different. So the easy example would be iron will either give away 2 electrons or give away 3 electrons. It normally gives away 3 electrons, and when it does that, then the iron's charge becomes +3. Or this one, the iron's charge becomes +2. So anything that does that, where it's either or, those guys are classified as Bs. And something like sodium, no matter what, when it reacts, it only ever gives away 1 electron, ever. So its charge is only ever +1. So it gets to be an A type atom because its oxidation state or its charge or the number of electrons it gives or takes is set in stone.
Okay.
But again, it doesn't really matter because as soon as enough people die, then that whole nomenclature system will go away. And that sounds harsh, but the reason it's sticking around is there's still a bunch of people that know it and they're teaching it because they've been teaching it for like 50 years. So an example of that would be, well, let's just do this one. This thing is now called iron. Well, maybe if I could spell. Iron 3. That's the name when iron loses 3 electrons. The old name was ferric. So you had to memorize that ferric meant that the iron lost 3 electrons. Where up here, naming it iron 3 is telling you, hey everybody, this iron lost 3 electrons. And this one is like, you got to memorize that ick means 3 electrons. And enough people have died that nobody's teaching this anymore. And so soon enough people will die and we won't have that A thing anymore, A and Bs.
Okay.
Okay, so the symbol on the periodic table is literally the abbreviated name of the atom.
Like for hydrogen, it's H.
The symbol,
That's the symbol.
the symbol for hydrogen is H. The symbol for carbon is C. The symbol for uranium is U. And most of the symbols make sense. There are 11 of them that don't make sense. Like sodium is Na. And it's because we've known about sodium for a long time, and it used to be called natrium in a different language. So for posterity's sake or historical significance, they kept the Na as the symbol, even though we call it sodium, and that doesn't make any sense. So there are 11 of them that are like that, and it's gold, potassium, sorry, it's sodium and potassium and copper, silver, gold, who else we got? Iron, tungsten. I can't remember the other ones off the top of my head, probably because they're not used very often. Antimony and tin, those guys are both, and lead. And the rest of them, oh, and mercury. And the rest of them make sense. Like their symbol, like zinc symbol is Zn. That makes sense. Nickel symbol is Ni. That makes sense. But there are some of them that don't make sense, and it's literally just because we're trying to honor the past. Okay, so the symbol is literally just the abbreviated name. The an element is a type of atom. So if you've got a tank, if you've got a balloon and the balloon's filled with helium, all the atoms inside of there are the element helium. But inside of there, there's a whole bunch of atoms, and all of those atoms are helium. Does that make sense?
Can you say that again?
So if you have
You have a tank.
let's say you went and you got some balloons, and the balloons were filled with helium. So inside that balloon is filled up with atoms, a lot of atoms, like a ridiculously large number of atoms, and all of those atoms are the element helium.
So, okay, so the symbol is the abbreviated name for helium, but helium is the actual element.
Correct.
Or the actual element. Okay.
And the element is composed of atoms, individual atoms.
Atoms.
So
they don't have to be helium, they're just atoms.
All atoms are one of those elements. It would be like you walking into the produce section and saying, everything in this produce section is, let's say you're in the fruit section. All of this over here is fruit. And then there's a banana.
and you could point to the bin and say, that's bananas. That's fine, but there are individual bananas, but you could also say that that whole thing is bananas. Does that make sense? But you could
Yeah.
just pull one banana off. So in the same way, I could say, that is a balloon filled with helium. And then I could reach in and grab one helium atom. I mean, I couldn't actually do that because they're too small, but you could reach in and grab some heliums. Does that make sense?
Yes, I get it now. Okay.
All right, what else we got? I don't know who's here. I don't know why I can't see everybody at the same time. Cancel. Manage participants. Oh, that's one way. Casey, Aurelia, Shane, anybody?
I just got back from checking my lab. What's up?
How's your lab going?
Well, foamy stuff on top and barely any change in the blue and stuff.
When the bubbles that make up that foamy stuff start to break, because they'll eventually lose surface tension and pop, then the balloon will fill.
Okay.
I think a lot of people that did this lab just set it up and went to bed and then looked at it in the morning.
Well,
Oh, I guess I got to start on mine.
Yeah, mine's been going for a few hours now, and my balloon's just barely, well, my rubber glove is just barely filled.
With that in mind, then, you don't mind if I turn that in tomorrow morning instead of tonight?
No, you're fine.
Okay. That's what you just said. I'm just going to leave that balloon on overnight then.
Yeah, you'll get a better response from that.
So it's okay if we turn them in the morning?
That'll be fine.
Okay.
Hopefully everybody's finished with the exam, or will be in what, 5 hours? Because that closes at midnight or 11:59 p.m.
Well, I hope no one forgets to do it.
So do you suggest for the next exam, if we go through the end of chapter questions, that we would be more prepared for the exam?
Yeah, what I've noticed so far is the people who have submitted longer summaries, like 5-6 pages, most of them have done significantly better than the people who have submitted 2-3 page summaries. It just feels like they read the material more carefully and then took better notes, which is the entire point of the summaries, is to take really good reading notes, because your exams are coming specifically from 2 chapters out of the text.
Of the 36 questions on the exam that I answered, I got 33 of them right. But it's like I just spent too much time getting caught up on the molecules.
Well, then you still did really well, so you're all right.
It's a B, so I was like, still kind of bummed about it.
Just one piece of the puzzle.
Yep.
Okay. Anybody else want to ask anything? Talk about anything?
Thank you.
Okay.
Did you guys see this thing that I put up today?
No.
What thing?
One sec. This one. Can you see that?
Yep.
Anybody got a problem with that?
I think you have carbon monoxide poisoning.
Ding, ding, ding. Yeah. I don't know what this bunch of retweets and likes are. I feel like there should be a million people right here saying, get the hell out of the house.
Kind of reminds me, like, especially with our area in the country, of like more people really do need to have radon detectors.
Yep. Yep, we're near a volcano and stuff comes up out of the ground, and you should I mean, it's not that you need a detector so much as you need to have detection done on your house, because it's not going to change. So if your house is susceptible to have radon intrusion, then you need an evacuation system, or you're just giving yourself cancer.
And that reminds me, it's you heard the stuff that's going on with asbestos, right?
Something different than mesomelanoma?
Yeah, looks like it's going to be up on the market again for certain products.
Oh, thanks, Donald.
But it was like quote unquote, it's like used for certain special applications only.
Well, it still gets used for brakes, for brake pads.
Yeah, but they are just furthering the products that are being allowed to use it.
Huh. I'm not seeing any of it. The EPA's new rule on asbestos goes short of a total ban. Yep. So they're just going to say it's okay to have in some things. The final ruling, 19 asbestos-containing products are okay. Some adhesives, sealants, roofing felt, oh well that's good to know, as well as millboard, pipeline wrap, reinforced plastics, and vinyl asbestos flooring. Alrighty. They will, oh.
Especially that flooring and the roofing.
Oh no. I got to read the whole sentence. Will be prohibited from entering the market.
Okay.
Okay, well, if nobody has any more questions, I guess I'll see you guys on Monday.
Yeah.
Okay.
All right, bye-bye.
Bye.
Have a good weekend.
You too.